Okay, so this problem reads, using energy considerations, calculate the average force a 60 kilogram sprinter exerts backwards on the track to accelerate from 2 meters per second to 8 meters per second in a distance of 25 meters. If he encounters a headwind that exerts an average force of 30 meters against him. 30 newtons. I can't read my problem today. 30 newtons against him. All right. So let's look at this problem using energy consideration using the work energy theorem. So we're going to remind ourselves that the net work acting on the sprinter is our change in kinetic energy. And so that is 1/2 the mass of the sprinter times his final speed minus 1/2 the mass of the sprinter times his initial speed. And so we can determine the change in kinetic energy from 1/2. We're told that sprinter has a mass of 60 kilograms. He goes from 2 to 8, so his final speed is 8 meters per second. And 1/2 times 60, and he started at 2 meters per second. So we can determine that the change in energy of this sprinter, the net work done, is 1,800 joules. So the work done on this sprinter is 1,800 joules. Now that's the net work. And so for us to appreciate what all the forces are that are acting on that sprinter, we need to draw a free body diagram. So let's draw a free body diagram of that sprinter. And what we really mean, of course, is sort of his body against the ground, pushing back on the ground. So the ground pushes him forward. So we know that the force of the ground is pushing him forward. There's a headwind in the opposite direction. So this is the force of the wind. We know that that sprinter has weight, and we know that that sprinter is on a horizontal surface, and so there's a normal force between the sprinter and the ground. So here are 4 forces. If I'm going to truly look at the net work acting on this sprinter, it's the sum of all these forces. The work done by gravity, the work done by the sprinter on the track, or the track, on the sprinter. So the work done by the ground on the sprinter. The work done by the normal force, and the work done by the wind. I almost wrote friction. So those are all the forces that could be doing work on the sprinter. Now, the motion of the sprinter is along that track. So we know that the displacement of that sprinter is along that track. So because of that, the work done by gravity and the work done by the normal force, since they're perpendicular to the displacement, those works are 0. And so our net work is the sum of the work done by the ground and the work done by the wind. So let's look at those 2 works. The work done by the ground. Well, that's equal to the force of the ground times the distance that the sprinter traveled times the cosine of the angle, which we know is equal to 0 in the same direction as the displacement. So if we simplify that, we find that we have the force of the ground times that we're told that they travel 25 meters, and that straight sprint, times the cosine of 0, which is just 1. All right, that's as far as we can go. And what about the work done by the wind? Well, that's the force of the wind times 25 times the cosine of the angle of the wind, which we know is in the opposite direction of the motion. And so the force of the wind, we're told the force is 30 newtons times 25, and the cosine of 180 is -1. So the force done by the wind is -750 joules. All right, so we're going to use our relationship to determine the force done the force done by the ground. So we have the net work, 1,800 joules, is equal to, well, that's 0, the work done by the ground, which is the force of the ground, times 25, plus another 0, minus or plus a negative 750, which is the work done by the wind. And if we solve for the force by the ground, I add my 750 to this side, divide by 25, and we find the force done by the ground is 102 newtons. All right, so recognizing that the net work is what's causing that change in energy, that net work is caused by all the forces acting on the object and the work that they do, two of which do 0. Determine what those works are by the other two, and we can solve for our force. All right, good job.